Hi guys, hope all of you are doing great today. So I'd like to welcome us to our channel of Honest Sciences and Mathematics TV channel. In our channel, we deal with the different aspects of sciences, mathematics, and perhaps some of the related topics. And today we are going to look at a topic in chemistry that basically deals with the concept in organic reactions, and this is oxidation levels. Now we're going to see that the allocation of oxidation numbers in organic chemistry is quite different from the normal chart that we normally allocate for cations and anions. And we are trying to create that difference in this specific discussion so that we are able to be able to choose reacting species and particularly reagents, especially when performing organic reactions. So for today, I'd like us to have a discussion on that specific topic. And I'd like to encourage more of our members to kindly subscribe to the group and join us in our discussion and various topics, especially on our comment section, so that we can be able to assist one another in trying to improve these skills and mathematics and sciences. So without further ado, I'd like to welcome all of us. Thank you and welcome. So today's discussion is basically going to be an emphasis on the concept of oxidation numbers, especially in organic reactions. Now we're going to create a contrast between oxidation levels in organic reactions and the normal oxidation that we assign to particularly cations and anions. Now in our discussion on the topics, various topics that we have handled in the concept of electrochemistry, this one in an essence gave us a clue on how we can be able to assign oxidation numbers, especially when we were dealing with the concept of redox reactions. And this is basically a short name for reduction and oxidation reactions that we had looked into, especially when we were dealing with the overall ionic equations. So in a sense, I'm going to give an example of this particular equation, and we're going to see how we can be able to assign oxidation numbers in normal reactions as contrasted to the organic reactions that we're going to see later, which is mainly our topic of discussion for today. Now suppose I have a reaction which is basically going to be considered a redox reaction, whereby iron is going to react with copper ions. Basically this ion an element which is going to react with the copper ions to form this particular ion. It's a charged particle now, plus the element, the copper, and this basically is a displacement reaction that we're going to see, but the overall reaction is a redox reaction, which means that it entails the aspect of reduction and oxidation. So therefore, if we try to write this particular equation in its state, so we're going to allocate this reacting species and the product species, their individual states as such. So if you try to write the individual ionic equation for this particular species for iron, we're going to see that the ion, which is a solid, is going to undergo a process which is going to lead to formation of ions, plus of course 2 electrons. Now from the reacting species, we're going to see that this is basically going to lose 2 electrons to form an ion. So there's a particular definition that we're going to use in referring to this concept of losing electrons, basically whereby we're going to see that in allocating the charge for the normal ions, which are basically solids, there's a rule of oxidation, of assigning oxidation numbers, whereby we're going to see that oxidation numbers of an combined element is 0, Ag in molecules and atoms, and numbers of all atoms is basically 0. So for us to figure the oxidation number for iron, which is a solid and combined element, basically it's going to be 0. And then when it is transformed into this specific ion, we're going to see that there's an increment of a positive 2. So therefore there's an increase. If per se we were trying to locate that one on a scale, then there's an increment from 0 to 2. So therefore this concept is being referred to as oxidation. So basically, if we try to define the concept of oxidation, is therefore the loss of electrons as such. So there was an acronym that we are using to particularly sum up this concept of oxidation insofar as electrons are concerned. And this was oil rig, basically standing for oxidation is loss of electrons, while reduction is gain of electrons. Now, suppose we try to look at the other way for the condition, or rather whatever that is happening with the copper, or the reaction that is happening with the copper. We're going to see that for us to illustrate the concept in this, we're going to have the copper ions, of course, forming, or rather gaining the 2 electrons from ion to form copper as solid. So this is aqueous. So from this particular case, we're going to see that there is the oxidation number in this particular case is going to change from 0 to a charged ion, which is from positive 2 to charged ion, which is 0. Therefore, there is addition of electrons in this particular case, and this reaction is going to be a reduction reaction. So therefore, if we have a combined reaction for which there's a reduction in the number of a charge for copper and the increment in the number of charge for iron, therefore we are going to have an oxidation reaction for the side of iron, and then there's a reduction reaction for the side of copper, and therefore the overall reaction for this specific reaction is known as a redox reaction, which basically I've indicated on this. So the process of assigning oxidation numbers basically relies on one of these rules that I've said, whereby if it's either gaining of electrons or losing, then we have to account for the number of electrons which has been gained, and therefore that will account for the overall charge over this particular reacting or the product species. Now there are elements which are going to be involved in this particular case. And for our first case, we are saying that this particular element of copper is going to be an oxidizing element, while iron is going to be a reducing element, since it's going to reduce copper insofar as its charge is concerned. Now from this, there are specific rules which are used to assign oxidation numbers in this particular reacting and species and product species. And we had mentioned one of the rules that for uncharged compounds or atoms or elements, as we have mentioned, the combined elements, the oxidation number of all the atoms is 0. And then we're going to see that the charge on an ion containing one element is equal to the oxidation number of that element. For instance, if I write magnesium 2 positive, and therefore the oxidation number of that particular element is 2 positive. Now that is going to form a summary in a way of the oxidation number that we normally assign for the cations and anions. And we're going to also to see now in our particular discussion for today, there are different ways in which we are going to assign oxidation numbers for organic compounds respectively. Now for organic compounds, we're going to see that the system of assigning these oxidation numbers for different reactions is quite different. And this is, of course, in contrast with what we have discussed for the case of assigning oxidation numbers for different anions and cations, as I had earlier said. Now, in trying to figure out whether there's a reduction process or oxidation which has taken place, then therefore it's going to assist us in different organic reactions to try to assign the reagents that we're going to use. And therefore we're going to look at the different examples that we can be able to use in demonstrating on how we can be assigning oxidation levels to this particular organic reaction. And one of them is we're going also to look at an example for how we can be able to transform different molecules, or rather maybe just having a reaction and then trying to identify what kind of reactions are taking place. Now I'm going to give a few rules which are going to be used in assigning oxidation number for organic reactions. Just as I said from the beginning, there are some specific rules which we are going to use in assigning oxidation numbers for cations and anions. Now for organic compounds, which basically we said they are formed by a fundamental element which is carbon. Now for organic compounds, we're going to identify each carbon atom that is, of course, contained in that specific element, and n changes that are going to accompany are to be realized within that carbon during a reaction. So basically this refers to the number of other elements which are going to be attached in this particular element of carbon, and therefore that is going to form a basis for us in assigning oxidation numbers. So for the first case, we're going to see that different atoms are going to be attached to this carbon atom in the reaction, and therefore basically we have seen that hydrogen is one of the most common atom that is going to be attached to these carbons. So in any case, if we find hydrogen attached, or if hydrogen is attached to a carbon, then therefore we are going to assign a charge of -1. So for any hydrogen atom that is attached to carbon, we're going to assign a charge of -1. But for other hetero atoms, and in this case I've mentioned about this particular concept in relation to carbon, whenever talking about heteroatoms, and this refers to the sulfur, nitrogen, oxygen, perhaps bromine, fluorine, chlorine, etc., which are going to be attached to the carbon atom, which are generally referred to as heteroatoms. Then we're going to assign a charge of +1. So if we identify any of these heteroatoms that have been attached to a carbon in this specific compound or the reaction for that particular reaction, then we're going to attach a charge of +1. And therefore we're going to see that this carbon atom has the ability, of course, as we said, to form double and triple bonds, and we're going to account for this whereby we're going to see how we can be able to perform these specific reactions. So therefore we are going to start this by, and therefore for the triple or double bond that is attached or maybe contained in this particular case for the carbon attachment to the carbon atom, we're either going to double the charge or triple it respectively, and this basically depends on the kind of this applies to the heteroatoms that I've mentioned in this previous statement. So this is a summary of how we're going to identify or rather assign oxidation levels to organic reactions, and I'm going to give a few examples so that we can be able to, of course, try to figure this one out. I've said that the assignment of these oxidation levels is different from the normal ones that we assign for cations and anions, and perhaps we can just give two examples which are going to assist us figure out why we need to, of course, rely on different rules insofar as organic compounds are concerned. Now suppose I have this specific alcohol and then it's undergoing a particular change, and we're going to have this particular compound at that specific level. We can just give this one a methyl group just for emphasis. This something that we need to consider in this particular case. Now if we try to look at this particular case, we're going to identify the atoms which are involved in this particular case, and I can be able just to expand this so that we identify the atoms which are attached to this particular element. So of course this is a different one, but just for the sake of illustration, I'm just going to show the carbon and the hydrogen at this specific point. And then at this point we have got a carbon atom and a hydrogen. So therefore we are going to consider the number of hydrogens that are present in this particular species before it is being transformed to another one, and that is going to assist us to identify the kind of reaction which is taking place at this specific point. So we had said earlier that this, of course, from the organic compounds series, we can identify this one as an alcohol, and this is an aldehyde. So there's a transformation which occurs from an alcohol to an aldehyde that we had mentioned earlier in one of our organic discussion on organic reaction. But for this one, I want us to identify either the kind of changes which have taken place. So therefore, we can see if this element contains carbon, hydrogen, and oxygen, and then this is also containing carbon, hydrogen, and oxygen. So therefore, the number of carbons in the first compound is 2, and then hydrogen is, this is a 3, 4, 5, 6, and then oxygen is 1. So this oxygen is 1. The number of hydrogens, these are just 4, and then we have got carbon 2. So if you try to look at carbons, they have been maintained and oxygen maintained, but there's a loss of hydrogen from 2 hydrogen from basically 6 to 4. Therefore, this one was a reaction that was taking place by loss of hydrogen. Basically, you can just assign that one the removal of 2 hydrogen from this particular point. So one of the processes that we can be able to use in formation of aldehydes is mild oxidation of primary alcohols. As we have discussed in one of our videos, we can just go and confirm that for the sake of clarity. And therefore, the loss of hydrogen is going to be referred to as an oxidation reaction. And therefore, this is going to form one of our first examples for discussion. Now, I'm going to do away with this first part so that we can be able to use a second example for that particular case. So if I have a compound, which is of course an alkene, and then it's being transformed into this specific compound, which is an alkane. This is a double bond, single bond respectively, so we can be able to outrightly identify this particular compounds. So if you try to look at this, this is a reaction that is accompanied by addition of hydrogens, and therefore there are 2 hydrogens which have been added into this specific reagent to form this final product. And this process is referred to as reduction. Whereas in our first case for ions and cations, we had anions and cations, we had said that oxidation of loss of electrons was being referred to as oxidation and reduction. In this case, the addition of hydrogen and the removal of hydrogen respectively is going to be referred to as oxidation and reduction as per these 2 illustrations respectively. So in this case, of course, we can be able to identify the kind of reaction, but I want us to look at the third example and try to classify it, whether it's an oxidation or reduction reactions respectively. Now, suppose I have a compound, this is a propane, and it's being transformed into an alcohol of that particular nature. So if you try to look at this, of course, in the first case, we can see that we have carbon and hydrogens at this specific point, and in this case, we have carbon, hydrogens, and oxygen. So basically, we can outrightly figure out that this basically there's an involvement of oxygen. So therefore, there's addition of oxygen atoms in this particular final product. And if we try to look at this is an alkene being transformed into an alcohol. Also, there's addition of hydrogen atoms in this particular case. In this case, we're going to have 2 hydrogen atoms being added to the final product. So in our first 2 scenario, we had a oxidation and reduction reaction that we are considering addition and the removal of hydrogen. But in a case whereby we are having a combined addition and oxidation reaction at that specific point, it will be difficult for us to contrast and say whether this is an addition reaction or an oxidation reaction. So therefore, in this sense, we're going to follow those particular rules. So a set of rules in trying to identify a way in which we can figure out oxidation levels for organic compounds. So I'm going to use 2 examples for this particular case so that we can be able to have a final way in which we can be able to represent these oxidation numbers in order for us to remove that ambiguity. So in this case, we are having a carbon at that specific point, and this is a primary alcohol that we used as an example in our first case. So we're going to have H3 at that specific point. So in us identifying these oxidation numbers, we had said there are various rules, and we said that for each attached hydrogen, we're going to assign a -1. So we're going to identify the hydrogens which have been attached at this carbon number 1. There are 3, so it is -3 for this attached hydrogen. So therefore, the overall oxidation level is going to be the sum of all the oxidation numbers in this particular compound. So we're going to have -3 attached hydrogens, and then for carbon number 2 we're going to have -2, since we have 2 hydrogens attached at this specific point. And as we said, we're going to consider atoms which are attached to the carbons, of course, in this particular compound. So this particular case, we have a direct attachment of carbon to oxygen. So therefore, we said for heteroatoms, we are going to consider that and assigning it a charge of +1 for an heteroatom of oxygen, as I've said. So this is going to have an overall charge of the summation over this particular set of charges. So this is going to be -4, which is going to be the sum of the charges of each molecule in this particular compound. Now this compound, this is ethanol. Now suppose we try to look at an aldehyde, which was the second product, of course, was the first product in our first example. So I'm going to consider an aldehyde, which basically is going to give us the condition for a double bond, which we had said was our third rule. That one is going to give us a sum of how we can be able to do that. So if we try to look at this, we're going to consider the number of carbons, as we said, in this particular compound, and identify the changes. So the oxidation number for the first one, which is a methyl group, is going to be -3. Since it's got 3 hydrogens attached to it, we said that 1 hydrogen is going to be assigned a charge of -1. So for the second one, we're going to have a -1 due to hydrogen attached to it. But there's an heteroatom which we said we assign a +1 with a double bond. So in any case, if there is a single bond, it is +1. But for a double bond, we are going to double that charge. And for a triple bond, for the sake of alkynes, then therefore we're going to triple that. But in this case, we're going to have two bonds for this carbonyl carbon. So therefore, it's going to be a positive 2 given as such. So therefore, we're going to see that this is for the hydrogens from the methyl group. This is for the hydrogen from the carbon group. And these are for the 2 double bonds. And therefore, this is going to be an overall charge of -2. So these are the basic rules that we're going to use in assigning oxidation levels for organic compounds and organic reactions, or perhaps the species which are going to be a product or reacting species in organic reactions. And this basically is going to assist us in trying to choose appropriate reagents, as we said, during organic reactions, and perhaps identify which step is an oxidation step or a reduction step, respectively. So I hope that we have understood, and we're going to contrast appropriately the kind of oxidation or the kind of reaction that is taking place in organic reaction, insofar as oxidation levels. To look at related videos, and check on our description box for a link for other videos that we have done on the same in this particular video. So that is it for today, guys. Bye. God bless you.